A fan develops 5.0-inch water static pressure and 0.7-inch water velocity pressure when the flow is 8,000 cfm of 100 degree Fahrenheit air. The shaft horsepower is 7.6 and the speed is 1,800 rpm. Calculate the static and mechanical efficiencies. We need first to get the total head by adding static head and velocity head together. Then, convert its unit into feet. We can now solve for the power by using the formula P is equal to gamma times Q times H, where gamma is the specific weight, Q for volume flow rate, and H for the total head. Since the total head is in water, we will use the specific weight of water, which is equal to 62.4 pound per cubic foot. Substitute all the given values and simplify. Then, convert it into HP. The shaft power is given, which is equal to 7.6 horsepower. Therefore, we can now solve for the mechanical efficiency. Substitute the given values into the mechanical efficiency formula and simplify. And we got the value of mechanical efficiency, which is equal to 94.61%. Now that we have the value of the mechanical efficiency, substitute the values into the formula. Static efficiency is equal to mechanical efficiency times static head over total head. And the answer is 83%. A manufacturer rates his fan at 4.43 inch of water static pressure for 6,000 cfm of 70 degree Fahrenheit air, 1,500 rpm, 29.92 inch Hg barometric pressure, 71% static efficiency. What will be the static pressure and shaft horsepower at 1,700 rpm, 200 degree Fahrenheit air, 26.0 inch Hg barometric pressure? First, we need to identify all the given values. We will now solve for the density using the formula density is equal to pressure over gas constant R times absolute temperature. Substitute the given values and simplify. Using the basic fan laws, we can now solve for the static pressure. To make formulation easier, the basic fan law can be illustrated into a table like these. Using the table, we can formulate an equation to solve the static pressure. Based on the table, under H, for N and D is 2, while for rho is 1. These numbers are the exponent we will use. We don't have diameters given, so we will ignore it. We now substitute the given values into the equation. Then, simplify. And we got the static pressure 2, which is equal to 3.97 inch water. Now we will solve for the shaft power for fan number 2. We need first to get the shaft power of the fan number 1. Just substitute the given values, then simplify, and we get 5.899 horsepower. Then, formulate again an equation using the table. Under P, N is 3, and for rho is 1. Substitute the given values and simplify. And the answer is 5.99 HP. A condensate pump at sea level take water from a surface condenser, where the temperature is 81.33 degrees Celsius, where saturated pressure equals 50 kilopascal, and specific weight equals 9.78 kilonewton per meter cube. The friction in the piping is assumed to be 2 meters. The pump's required head is 2.75 meters, and the pump's centerline is 4.75 meters above the water surface. Is there any cavitation? Justify your answer. As stated in the problem, the net positive suction head required is equal to 2.75 meters. The friction loss in pipes is 2 meters and a pump centerline of 4.75 meter. We will now solve for the net positive suction head available using this formula. Since it is a surface condenser, we will cancel out the pressure head in the equation. Then, substitute the values into the equation and simplify. And we got NPSHA, which is equal to 2.75 meter. NPSHA is equal to NPSHR, therefore, there is no cavitation. A double suction, single-stage centrifugal pump delivers 4,000 GPM of seawater from a source where the water level is 8.5 feet below the pump's centerline. The pump discharges into a surface condenser 10 feet above the pump's centerline. The shaft speed is 1,750 RPM. What type of impeller should be used? See table below. First, we need to illustrate the problem. Then, identify all the givens based on the illustration. It is stated in the problem that the pump is a double suction pump, so we need to divide the volume flow rate by 2. For the total head, we just need to add suction and discharge head together. We can now solve for the specific speed using the formula Ns is equal to N times square root of Q over H raised to 3/4. Where N is the shaft speed, Q is the volume flow rate and H is the total head. Substitute all the given values and simplify. And we got 8,773.53 RPM. Based on the table, the impeller type that should be used is axial. A two-stage single-acting compressor is to deliver 90 pounds per min of air from 14.3 psia and 90 degrees Fahrenheit to a final pressure of 185 psia. The normal barometer is 14.64 psia and the temperature is 80 degrees Fahrenheit. The temperature of the air at the exit of the intercooler is 90 degrees Fahrenheit, the speed is 210 rpm, and PV raised to 1.34 equals C during compression and expansion. The clearance is 5% for both cylinders. The temperature of the cooling water increased by 18 degrees Fahrenheit. Find A, the volume of free air in CFM, B, the mass of cooling water to be circulated through the intercooler in pounds per min, and C, the shaft power in horsepower if the mechanical efficiency is to be 85%. We need first to illustrate the problem. Then, identify and label the givens. To solve for the volume of free air, we need to use this formula. The actual volume or V1 prime is not given, so we will need to solve for it. Substitute all the values and simplify. And we got the answer. 1,229.66 cubic foot per minute. We will now solve for the mass of the cooling water using this heat balance equation. Temperature 2 is not given, so we will need to find it first. Again, pressure 2 is not given, and we need to find it. P2 and P3 is equal to Px, which is the intercooler pressure. Substitute P2 and the other given and solve for T2. Now that we all have the givens for the heat balance equation, we can now solve for the mass of cooling water. Simplify the equation, and we got the answer, which is equal to 253.248 pound per minute. To solve for the shaft power or brake power, we will use the formula BP is equal to compressor work over mechanical efficiency. We need to solve first for the compressor work using this formula. Substitute the given values into the formula and simplify. We can now solve for the shaft power by substituting the compressor work and mechanical efficiency into this formula. Simplifying it, we will get the answer which is equal to 284.69. The air duct system is shown. The static pressures at A and C are 13.4 and 4 mm of water respectively. Using friction chart and equal pressure drop method, determine the diameter in lengths AB, BC, branch BE and branch CD. Consider friction losses only. Note, lengths are in meters. We need first to determine the static pressure at A to C. Static pressure at AC is equal to the static pressure at A less static pressure at C. Substitute the givens then simplify. Static pressure at AC is equal to 9.4 mm of water. We also need to determine the friction loss at AC. Friction loss at AC is equal to static pressure at AC over length of AC in meters. Substitute then simplify. And we got 0.1 mm of water per meter. Friction loss at AC is equal to the friction loss at AB and BC. The volume flow rate at length AB is not yet divided by the branches. Therefore, the volume flow rate at AB is equal to the total volume flow rate, which is equal to 7 cubic meter per second. Now that we have the value of friction loss and volume flow rate, we can now determine the diameter by using friction chart. Based on the friction chart, at 7 cubic meter per second and 0.1 mm of water per meter, the diameter is equal to 950 mm. At length BC, the volume flow rate is equal to 3 cubic meter per second. Using friction chart, at 3 cubic meter per second and 0.1 mm of water per meter, the diameter is equal to 700 mm. This time, we need to find the static pressure at BE. The static pressure at BC is equal to 3 mm of water. Using the formula static pressure at BC is equal to static pressure at B less static pressure at C, we can get the value of the static pressure at B which is equal to 7 mm of water. To solve for the static pressure at B, we will use this formula. Static pressure at B is equal to static pressure at B less static pressure at E. Point E is at the exit. Therefore the static pressure at E is equal to 0. Static pressure at B is equal to 7 mm of water. At length BE, the friction loss is equal to 0.23 mm of water per meter and the volume flow rate is equal to 4 cubic meter per second. From the friction chart, at 4 cubic meter per second and 0.23 mm of water per meter, the diameter is equal to 675 mm. Determine the static pressure at CD using this formula. Point D is at the exit, therefore the static pressure at D is equal to 0. And we get the static pressure at CD which is equal to 4 mm of water. At length CD, the friction loss is equal to 0.13 mm of water per meter and the volume flow rate is equal to 3 cubic meter per second. Using friction table, at 3 cubic meter per second and 0.13 mm of water per meter, the diameter is equal to 675 mm. Design of R134 air refrigeration system which comprises of 2 evaporators at different pressures with single compressor, individual expansion valves and a back pressure valve. The pressure in the low pressure evaporator, high pressure evaporator and condenser are maintained at 140 kPa, 320 kPa, and 900 kPa respectively. The pressure at the inlet of the compressor is 140 kPa. The low pressure and high pressure capacities are 100 kilowatts and 75 kilowatts respectively. The refrigerant leaving the evaporators are dry and saturated, and compression is isentropic. Determine the COP of the system. To understand the problem better, we need first to illustrate the schematic diagram. Using our 134A table, find the enthalpies required to solve the problem. For state 3, 4 and 7, their enthalpies are equal because they are only separated by expansion valves. For their enthalpies, the saturated liquid, or HF at 900 kPa is equal to 101.61. State 5 and 6 are also equal because of the expansion valve. From the table, the saturated vapor, or Hg at 320 kPa is equal to 251.88. For state 8, the saturated vapor, or Hg at 140 kPa is equal to 239.16. We will now solve for the mass flow rate using the formula. Mass flow rate is equal to evaporator capacity over change in enthalpy. At low pressure evaporator, mass flow rate at state 7 is equal to evaporator capacity over H8 less H7, where the evaporator capacity is equal to 100 kilowatts and the change in enthalpy is 239.16 less 101.61. Simplify, and we get the value of M7, which is equal to 0.7270 kilograms per seconds. Mass flowing at state 7 is also equal to the mass flowing at state 8. At high pressure evaporator, mass flow rate at state 4 is equal to 75 kilowatts over 251.88 less 101.61. Simplify, and we got the value of M4, which is equal to 0.4991 kilograms per second. Mass flowing at state 4 is also equal to the mass flowing at state 6. Find the enthalpy at state 1 using heat balance equation. Substitute the values into the equation and simplify. And we got the value of H1, which is equal to 244.34. We will now solve for the entropy at state 1 using interpolation. From our 134A table, at 140 kilopascal and H equals to 244.34. The values are listed in the table. To interpolate the given values, use mode 37 of the calculator. And we got the answer, which is equal to 0.9646. State 1 and 2 are isentropic, therefore their entropies are equal. Now, we solve the enthalpy at state 2. Again, from the table at 900 kilopascal and S2, the values are listed in the table. Using calculator, we interpolate the givens in the table and get the value of H2, which is equal to 284.26. We will now solve for the compressor work using the formula WC is equal to M1 times H2 less H1. Substitute the given values and simplify, and we get 48.95 kilowatts. All the needed values are now available. So, we can now solve for the COP of the system. We will use the formula COP is equal to total evaporator capacity over compressor work. Substitute the values, then simplify. And we got the value of COP, which is equal to 3.57. That's all. Thank you.